All right, lesson 56 talks about related rate problems. This is where derivatives come in handy. A related rate problem is a problem where one or more related quantities are changing. So for example, not in this case, but let's say you had the bathtub getting filled up and you also had the plug or the drain open, and the tub is filling up at a certain rate and it is draining water at a certain rate, and you want to know how full the bathtub would be maybe in 30 minutes. It's called a related rate problem. We're going to write the related equation that relates the variable to the problem, differentiate it, and substitute the information in. Do not substitute until you're ready to. So here we have a 13-meter long ladder. So this is 13 meters. It leans against a vertical wall. The base of the ladder is pulled away at a rate of 1 meter per second. So it's pulled this way, 1 meter per second. Find the rate at which the top of the ladder is falling. So we're looking at finding this rate, which it's falling, when the base of the ladder is 5 meters away. So what we're looking at is this is dx dt, and we want to find dy dt. Rate is always a derivative. So now what I've got here is a triangle. So x squared plus y squared equals 13 squared. Good old Pythagorean theorem. And now what we have here is our equation. That is our related equation. We're going to take differentials. 2x dx plus 2y dy equals 0. Now I'm going to divide everything by dx and solve for dy. So now we have 2y dy dx is negative 2x, and then dy dx is going to be negative x over y. Now that's what our related rate equation is. And we're doing this by dt, not dx. So what we're going to do is we're relating it to distance over time. And if that's the case, the dx dt does not go away. Now we have to find out what's this rate when x happens to be 5. So if x is 5, we need to solve for y. What will y be when x is 5? So I have 5 squared plus y squared equals 169. Y squared is going to be 169 minus 25, which is 144. So y is going to be 12. We'll ignore the negative because we will never have a negative distance. So when x is 5, y is 12. Now we're going to the left. So what we could say here is we've got negative 5 and 12. We'll leave it this way because this is going down, and we're just going to call this a positive x direction, and we said this went at 1 meter per second. And this is meters over meters, so those cancel, and we end up with negative 5 over 12 meters per second as the related rate. That's how fast this ladder is going down this wall when x happens to be 5. It's not always going at that rate, but only when x is 5. Okay, we have a 6-foot tall man, so this is 6 feet, and he's walking straight away from a 15-foot street lamp. At what rate is his shadow lengthening? This is his shadow, so we're looking at dl dt when he is 20 feet away from the street light. And he's walking away at this rate, 4 feet per second. So he's walking away at a rate of 4 feet. So this direction, and that's dx dt, and he's going 4 feet per second. And this is what we're looking for. Well, we have to find a related equation. So let's look. We have two triangles. They're proportional, so why don't we try L plus x. This distance is to 15, as L is to 6. Now I have my related equation. I need to simplify this equation, so why don't we cross multiply, put like terms together, and let's see, do we want to solve for L or do we want to solve for x? We want to find dl dt, so let's solve for x. X is going to be 9L over 6, which is 3L over 2. So there is my related equation. Now I'm going to take derivatives. So I start off with 3L over 2 equals x, and I'm going to have 3 halves dl is to dx, divide everything by dt, and we're going to solve for dl dt. So his shadow is growing at a rate of 8/3 feet per second. Okay, we have a typical cone, kind of like an ice cream cone. It has a height of 9 centimeters, and this diameter is 6, so right away the radius is 3. It's leaking water, so there's water that's dripping out here, and it is dripping out at a rate of, and the reason I know its volume is it's cubic centimeters per minute. It's leaking out. So I'm going to call that negative because that's what's leaving the cone. Find the rate at which the water level, H, is dropping when H equals 3. So what we're looking for is dH dt when H equals 3. That's what we're looking for. So we have to find a related equation. The hardest part about these related rate problems is they don't give you the equation. You have to look and see what you can decipher out of this. Well, I'm going to see how I'm going to relate 3 is to 9 as, and this is 2r, so this would be r, little r, is to h. So 9 is the big one. Let me draw this better. This is 9, and there's h. So these are proportional triangles. So I could say r is to h as 3 is to 9. And I want to solve for r, so 9r equals 3h, and r equals h over 3. There's my related equation. Well, at least there's my r. Now this is a cone. The volume of a cone is going to be 1/3 pi r squared h. Now, if I start taking derivatives right now, I'm going to get dRs and dHs, and I didn't get anything related to dRs. So I want to get rid of that r. I want everything in terms of h. So what I'm going to do is substitute what r equals. H over 3 squared, and now I get 1 over 27 pi, and this would be h cubed. Now, here's my equation. I needed the r, so all I had to do was have h's. So now I'm going to write this over here, since I'm running out of space, and I'm now going to take derivatives. Differentials, I mean. dv is equal to pi over 27, 3h squared dh, divide everything by dt, and I need to find dH dt. Before I do that, let's do some simplifying. So I've simplified this. We've got 3 going into 27 9 times. So now I have pi h squared dH dt, and I need to solve for dH dt. So when I do that, I've got dv dt over here, 9 over pi h squared. And now what I'm going to do is I'm going to plug in a -1, 9 over pi 9 squared. I end up with -1 over pi. Sorry about running out of space. And this is dH dt, so I'm looking at centimeters per second. You could plug that into your calculator and actually get a decimal if that's what you'd like, which is -0.32 centimeters per second. Sorry about the crampedness.